Hello, people, for real, in our space, for the first time in 2 years, sitting in our space for the first time in 2 years. We had people standing. Welcome to the Rare Book Manuscript Library. So really, welcome. I'm Caroline Sinovich. I'm one of the curators here. I'll do the RBML honors. So welcome once again to the first public event, seated public event in our space in 2 years. We're so happy to be able to host public back. We're so happy to be able to have an actual exhibition with actual books out in the same room as our readers, our visitors. Thank you for coming. Thank you for coming because of the weather. It's Thursday, so it's snowing, right? It's snowing every Thursday. So today we're going to have a speaker, and we have a selection of books related to the talk and the exhibition. So the books will still be out after the lecture, so you're welcome to come and still browse. Just want to acknowledge Professor Willy Gentner, co-curator of the exhibition, together with my colleague Rutan Maori, who's hiding at the desk over there, and our colleague Marco Valderes Perez from the Conservation Department, who helped stage the exhibition. It was really like a big trio work. And our colleague Anna Rodriguez is not here today. Maybe not, who also helped with all the imaging. It's fabulous. So I'm just going to turn things over to Willy Gentner, Department of Geology, who will introduce the speaker, and we can take over afterwards. So thank you.
Thanks. Thanks everyone for coming. So it's my pleasure to introduce Professor Marcia Bjornerud, who's going to be the keynote speaker for this exhibit here at the Rare Book Manuscript Library. Professor Bjornerud is the Schober Endowed Chair in Environmental Science, Professor of Geology at Lawrence University in Appleton, Wisconsin. Just a little bit about her background. She got her undergraduate degree at the University of Minnesota, master's and PhD at the University of Wisconsin-Madison. After that, she was the Bird Polar Research Center postdoctoral scholar at the Ohio State University. She joined the faculty at Miami University and then moved to Lawrence, where she is right now. Her research is in structural geology and tectonics. In particular, has focused and is still focused on ancient mountain belts in places such as Svalbard, Ellesmere Island, northern Wisconsin, and the Upper Peninsula of Michigan. She's been a Fulbright scholar at the University of Oslo in Norway and the University of Otago in New Zealand, and is a fellow of the Geological Society of America. This talk is a little bit unique, at least for the Department of Geology. It's going to be not so much focused on a research talk, but is more going to be focused on the history of geology, geologic time, Earth history. And for that, Dr. Bjornerud is very well suited to be the presenter for this. She's an author of several books and numerous articles in the New Yorker, including this one, Timefulness, published in 2018, which received numerous accolades and was a finalist for the Los Angeles Times Book Prize for Science and Technology, and was longlisted for the PEN and E.O. Wilson Prize for Literary Science Writing. I'd highly recommend it if you haven't read it. It's a great combination of history and personal perspective, and is really a treatise on the importance of thinking like a geologist, thinking in terms of geologic time, Earth history for individuals and societies, especially as we confront the strange new world of the Anthropocene. So without any further ado, Professor Bjornerud.
I need to use this or not? Probably. Should I? Okay. So thank you, Willy, and staff of the Rare Book and Manuscript Library, and Anna and Max, and everyone in the department for inviting me in glorious 3D. Although we've been spending far too much time on screens in the last 2 years, it's unlikely that you would find anyone, even the most obdurate flat earthers, who would insist that the world is in fact only two-dimensional. Such a world was the premise of Edwin Abbott's classic, but offensively and unnecessarily misogynistic thought experiment of a novel, Flatland. I don't know how many people were exposed to this. I actually read it in a math class, and I thought it was interesting, but it's really quite offensive in some ways. I'll explain it in a second. Anyway, The characters in the book are intellectually cramped by their incapacity to imagine three-dimensional objects or spaces. The narrator is one of only a few citizens to recognize through dreamlike visions and an encounter with a quasi-divine presence called the sphere, that Flatlanders in fact occupy only one plane within a much larger three-dimensional reality. Elites in the government are apparently aware of this, but actively suppress the dissemination of the idea of a third dimension. And the narrator is actually telling his story from a cell where he has been imprisoned for his dangerous knowledge. It's an interesting conceit and a potentially powerful political allegory, but unfortunately Abbott makes his point through the intellectually cramped social hierarchy of his own time and place that was published in 1884. He depicts, for example, women as only one-dimensional linear characters, not even fully able to grasp the two-dimensionality of men and boys. So I don't know if you can see it from where you are, but this is the entrance for the women. They just need a narrow, like needle-like one, whereas the boys are different polygons. Anyway, I mentioned Flatland despite its less than enlightened presuppositions, because in some ways, we too live in a culture that struggles to recognize an entire dimension that gives shape to our lives, namely time. In fact, we as a society may be even more obtuse than the ignorant Flatlanders, because although we have plenty of opportunities to glimpse time, we actively choose, indeed make strenuous efforts to deny its existence, for a whole spectrum of reasons, ranging from personal vanity and fear of death to religious orthodoxies and capitalist fantasies. Meanwhile, geologists, like the narrator of Flatland, have for 2 centuries been patiently assembling evidence and trying to convince our fellow citizens that time is real, powerful, and very, very deep. Mapping deep time, building and calibrating the geologic timescale is among humanity's greatest but least appreciated intellectual achievements. And I'm so pleased to be part of this celebration of this largely unsung work. It's important to acknowledge that my comments and this exhibit focus on the evolution of geologic thinking in the West. I hope that there will be more scholarship available in the future on the evolution in other parts of the globe, evolution of geoscience thinking in other parts of the globe, where the Bible did not shape and cramp thinking about the history of the natural world. But it is true that the geologic timescale, as we know it, began to take shape in Britain and Western Europe in the late 18th century. My central thesis today is that charting deep time is not just a triumph of scientific reasoning, but in fact a feat of extraordinary imagination, a conceptual leap akin to the challenge Flatlanders faced in envisioning a third dimension. So let us follow the intellectual arc that took us from an Earth that was thousands of years old to one that was perhaps infinitely old, to one whose age was finally quantified as finite, but immensely great. I'm reflexively skeptical when someone is referred to as the father of a discipline or idea, but I think the designation father of modern geology is legitimate for James Hutton. He understood in his bones what rocks meant in a way that almost no one before him had. In some sense, his contributions can be compared with those of Newton, who showed that the heavens and the earth are not disjunct realms, but governed by the same physical laws. Hutton similarly demonstrated that the present and the past are of a piece, also governed by the same laws and processes. However, I don't think that most geologists are aware that Hutton's motivations and methods were not entirely in line with the standards of modern scientific inquiry. Today, most people who encounter Hutton's ideas read them as they were transcribed by his friend John Playfair, who's about a generation younger, another polymathic Scotsman, in his 1802 volume, Illustrations of the Huttonian Theory of the Earth, published about 13 years after Hutton's death. And that's the work in which the famous lithograph of Hutton's unconformity appeared. Playfair, a natural philosopher and geometrician, came from an accomplished family that included brother James, a noted architect, and William, an early statistician who gave the world pie charts and bar graphs long before they were menu options and spreadsheets. The conventional wisdom among geologists has long been that John Playfair liberated Hutton's brilliant thinking from Hutton's convoluted writing. But as someone who regularly pontificates to students how good writing and clear thinking go hand in glove, I've always found this suspect. Hutton's writing is certainly florid by 21st century standards, but not much more than Playfair's. Indeed, I find many of Hutton's turns of phrase rather beautiful. The most famous sentence from his 1788 treatise, Theory of the Earth, is sheer poetry. The result, therefore, of this physical inquiry is that we find no vestige of a beginning, no prospect of an end. And the opening words of the theory of the Earth are more inspiring than the first lines of most modern geology textbooks, with the exception of Steve Marshall. Here's the quote from Hutton. When we trace the parts of which this terrestrial system is composed, and when we view the general construction of those several parts, the whole presents a machine of a peculiar construction. Where so many living creatures are to ply their respective powers, we are not to look for nature in a quiescent state. Matter itself must be in motion, and the scenes of life a continued or repeated series of agitations and events. To me, this evokes a remarkably modern sense of the workings of a tectonically and biologically active planet, and the truly radical idea that the boundaries between animal, vegetable, and mineral are fluid. Reading further, however, one begins to suspect that Playfair's real editorial interventions to ensure Hutton's legacy were not merely stylistic, but substantive, namely excising Hutton's frequent assertions that these natural marvels reveal divine wisdom. For example, after a rapturous paragraph on how wonderfully Earth's climate and soils are suited to support life, Hutton states, "There is not any particular respecting either the qualities of the materials or the construction of the machine more obvious to our perception than are the presence and efficacy of design and intelligence in the power that conducts the work." This is awkward. The father of geology invoking God the Father. In fact, Hutton's was only one of several 18th century theories of the Earth, most of them blatantly teleological and almost comically Panglossian. But among these, only Hutton's work survives, despite his embarrassing invocations of providence, because he was right about so many things. At a time when leading geologists from Europe asserted that all rocks had been deposited in water, Hutton grasped the essential concept of the rock cycle, in which pre-existing rocks may be eroded and redeposited in sedimentary strata, or contorted in mountain building to become metamorphic rocks, or melted to form igneous bodies in an endless process of reincarnation. He had an impressionistic idea that the solid crust of the Earth was periodically reworked and split asunder by a great subterranean heat source more than 150 years before plate tectonics was understood. He understood the central role of biological processes in geologic phenomena, from rock weathering to the formation of limestone, something that would not be fully appreciated for almost 2 centuries with the emergence of the field of biogeochemistry. Less clear is whether these ideas were preconceived notions or the result of careful study of rocks, or some messy combination. In his book, Time's Arrow, Time's Cycle, the late paleontologist and writer Stephen Jay Gould argued that Hutton had already had the idea of an unimaginably ancient self-repairing Earth when he saw the famous outcrop at Sicker Point, that is the celebrated birthplace of deep time. Hutton was part of the landed gentry, and as a gentleman farmer, keenly aware of soil loss from his property each year. Like many Enlightenment thinkers, he was a deist and was troubled by the idea that God would allow the Earth to be steadily worn down by erosion, making it eventually uninhabitable. So long before he found the famous outcrop at Sicker Point, he was actively looking for evidence of rejuvenation. Some of Playfair's accounts of outings with Hutton do seem to support Gould's charge that Hutton drew conclusions, then looked for corroboration. Playfair describes a trip to Glen Tilt in the rugged Cairngorm Mountains of Scotland, where Hutton found evidence for his concept of subterranean igneous intrusions. Namely, he recognized fingers of granitic material that had made inroads into sedimentary rock in a manner that could not be explained unless the material had been molten at the time. In Playfair's words, describing Hutton, "In the bed of the river, many veins of red granite were seen traversing the black micaceous schistus. The sight of objects which verified at once so many important conclusions in his system filled Dr. Hutton with delight, and as his feelings on such occasions were always strongly expressed, the guides who accompanied him were convinced that it must be nothing less than the discovery of a vein of silver or gold that could call forth such strong marks of joy and exultation." We get a glimpse here of Hutton as a single-minded zealot. But the paradox remains that Hutton, in fact, got very close to the truth in a way that many geologic ideologues before and after him did not. Also, I and probably many of the other geologists in the room can attest from personal experience that most of us have whooped in exactly the same way upon discovering rocks that confirmed a partly formed idea. For me, this anecdote, more than any other, brings Hutton fully to life. I recognize his pure joy in having sensed the logic of the earth. The episode at Glen Tilt occurred in 1785, 3 years before Hutton visited the famous outcrop at Sicker Point, where he grew giddy from glimpsing the abyss of time. So it's pretty clear that he had already developed the idea of a self-renewing Earth powered by a great internal heat engine before he ever saw the unconformity there. And I don't hold it against him. He sniffed it out and conjured it in his imagination, even before seeing unambiguous proof. He had already envisioned deep time. So Hutton gave us both deep time and a prescient glimpse of how the solid Earth works. And for that, he deserves his place in the pantheon of geologists. But preoccupied as he was with the kind of beautiful idea of an endlessly cycling Earth, he was not particularly interested in creating a chronology of events that shaped the world, or with calibrating the geologic timescale. This abstract, cyclical vision of Earth time was not theologically threatening. It could still coexist with the realm of divine wisdom. And for a time, the idea of ancient worlds embodied in this famous lithograph of Hutton's Unconformity captured the public imagination in the way that space exploration does today. The public appetite for geology was heightened even further by Charles Lyell's Principles of Geology, published in 3 volumes in the 1830s, and of which I think we have the 2nd edition in the room next door. Lyle, a lawyer by training and an accomplished orator who made long speaking tours across Europe and the United States, speaking in Midwest cities and their opera houses, wrote about the emerging field with style and vivid imagery. One of my favorite quotes from Lyle is this passage, which I think any geologist will find resonant. Although we are mere sojourners on the surface of the planet, chained to a mere point in space, enduring but for a moment of time, the human mind is not only enabled to number worlds beyond the unassisted ken of mortal eye, but to trace the events of indefinite ages before the creation of our race, and is not even withheld from penetrating into the dark secrets of the ocean or the solid globe, free like the spirit which the poet described as animating the universe. This captures beautifully the second sight, the imaginative powers that are such an important part of the practice of geology. Hutton may have been aware of the dangerous psychological and theological implications of the new science of geology, even as he made the case for an incomprehensibly ancient Earth. The vanished worlds whose secrets he vividly reveals are entirely disjunct from the modern realm of humans. In an interesting analysis of Lyell's influence on Victorian culture, the literary scholar Michael Tomko argues that Lyle intentionally downplayed the potential psychic threat posed by the new geological worldview by introducing a strict, impassable division between the natural and the spiritual. Lyell's tactical maneuver of keeping the human mind and soul at safe remove from physical phenomena was temporarily successful, allowing geology to enjoy 2 decades of unconditional love, because the first editions of Principles of Geology did not mention biological evolution, nor especially human origins. In fact, at the time the first edition was published, many geologists had not yet accepted the idea that fossils even represent extinct species, as opposed to the remains of dead individuals with still existing lineages. And Lyle himself apparently did not believe that life forms had evolved over all the eons about which he waxed so eloquent. However, Principles became an immensely important influence on Charles Darwin. The first volume was in fact among the small cache of books that Darwin brought with him on the Beagle. And eventually Darwin changed Lyell's mind about evolution. More about that in a minute. But evidence for the surprisingly wide reach of Lyell's principles, well beyond the circles of Victorian gentleman scientists, comes from this lovely excerpt from Mark Twain's Autobiography, in which he describes a grizzled old riverboat captain he once worked for. So here's the quote from Twain. Being a chief mate, he was a prodigious and competent swearer, a thing which the office requires. But he had an auxiliary vocabulary which no other mate on the river possessed, and it made him able to persuade indolent roustabouts more effectively than did the swearing of any other mate in the business. Because while it was not profane, it was of so mysterious and formidable and terrifying in nature that it sounded 5 or 6 times as profane as any language to be found on the forecastle anywhere in the river service. He had no education beyond reading, and something which so nearly resembled writing that it was reasonably well calculated to deceive. He read, and read a great deal, and diligently, but his whole library consisted of one single book. It was Lyle's Geology. And he stuck to it until all its grim and rugged scientific terminology was familiar to his mouth, though he hadn't the least idea what the words meant. All he wanted out of those great words was the energy they stirred in his roustabouts. In times of extreme emergency, he would let fly a volcanic eruption of the old regular orthodox profanity, mixed up and seasoned all through with imposing geological terms, then formally charged his roustabouts with being old Silurian invertebrates out of the incandescent Andesdactylus post-Pleistocene period and damn the whole gang in a body to perdition. So we know that Lyle's Geology was on two famous boats, or two boats, the Beagle and a Mississippi steamer. So as I mentioned, Lyle's principles was tremendously important in shaping Darwin's thinking. The 3 volumes are essentially one long argument for the power of slow incremental processes to accrue into great changes over time, exactly what Darwin imagined for evolution by natural selection. And it was the application of this powerful geological idea to the biological realm that caused geology to come into conflict with religious doctrine. Darwin's dangerous idea that all life forms, including humans, had evolved from a common ancestor was, of course, threatening to church teachings, and from the moment Origin of Species was published, the question of quantifying Hutton's and Lyell's deep time became freighted with theological importance. Just need a drink of water. The physicist, Lord Kelvin, William Thompson, father of thermodynamics, the Einstein or Stephen Hawking of his day, also soon weighed in on the subject. He rightly dismissed Hutton's idea of an infinitely old, perpetually recycling Earth as a violation of the laws of thermodynamics, essentially a perpetual motion machine. But then he went further and brought an end to geology's early golden days. Over the course of several decades, Kelvin issued a series of papers estimating the age of the Earth based on calculations of how long it would take for the Earth to cool down from a molten state, and also how long the sun could have been burning, of course, long before physicists actually understood what made the sun radiant, namely nuclear fusion. Kelvin's estimates started at around 400 million years in 1860, the year after Origin of Species was published, and grew progressively shorter, plateauing at around 20 million years. Kelvin's primary argument was that the Earth is hot, there's high heat flow emanating from its crust, and therefore it must be young. We now realize, of course, that his determinations were based on faulty assumptions, namely that the Earth cools mainly through convection, not conduction, and also that it has a source of new heat, radioactive elements that are particularly abundant in the continental crust where he measured heat flow. But Kelvin's formidable mathematical prowess was intimidating to geologists of the day, who could only splutter that 20 million years simply was not enough time for all the events they were documenting in the rock record to have unfolded. Darwin called Kelvin his sorest trouble and died with real doubts about whether his own ideas could be true on an Earth that was only tens of millions of years old. It's actually amazing to me that Darwin and other 19th century geologists had some sense that the Earth had to be hundreds of millions to billions of years old before there was any understanding of the basis for genetic variation or any way of quantitatively calibrating the rock record. How did they know this? And I'm flashing this chart at you a couple of times. I just made a logarithmic scale of years, starting with the sort of 6,000 of biblical literalism. Some early geologists thinking, well, maybe the Earth's a bit older, and then Hutton thinking the Earth is infinitely old off the scale, and then having it crash down with Lord Kelvin at around 20 million years. Anyway, this sense that the Earth had to be on the order of hundreds of millions of billions of years old is a sign, I think, of their imaginative powers developed from close study of rocks and fossils, and in Darwin's case, finches, pigeons, beetles, and worms. They have developed a kind of scientific second sight that does not conform to the scientific method, but often proves correct. Nobel Prize-winning biologist Barbara McClintock, who discovered the molecular phenomenon of genetic recombination during meiosis, simply by studying kernels in maize for decades, called this a feeling for the organism, a leap of imagination, but imagination shaped and constrained by careful observation. It's worth mentioning that modern historians of science have discovered correspondence suggesting that Kelvin Meanwhile, a devout Christian had religious motivations of his own and was using his scientific reputation to cast doubts on Darwin's ideas. Kelvin's pronouncement that the age of the Earth could not be greater than 20 million years ended geology's early golden age and sent it into a decades-long period during which several generations of geologists were forced to suppress their own instincts and imaginations. Geology was also damaged in another way by Kelvin's decree. Geologists developed a distrust and distaste for physics and began to separate themselves from the other sciences. Young geologists weren't trained as rigorously as they should have been in physics and math, a legacy that unfortunately persists to some degree today. As the 19th century went on, physics continued to triumph while geologists either focused myopically on taxonomy rather than grand unifying theories, or attached themselves to the grimy business of locating coal and ores to fuel the roaring economy of the Gilded Age. So that by the late 19th century, geology had acquired a tainted reputation as a lesser sort of science, while the success of physics caused its methods to become the template for all other sciences. But I think there's another more stubborn reason that physics attained and retains its position at the apex in the hierarchy of science. Physics, and also chemistry, are tellingly called pure sciences because they lay claim to universal, eternal truths that are effectively outside time. By this reckoning, biology and certainly geology, which are thoroughly steeped in time and what Stephen Jay Gould called historicity, are by definition highly impure. These ideas have deep roots in Western thinking, traceable, I think, back to the Greeks and their concept of nested celestial spheres, with the spheres of divine truth being furthest from the mundane, corrupt, changing earthly realm. 3,000 years later, we still privilege fields that focus on phenomena unburdened by time and messy histories. The ecologist John Hart has suggested a useful contrast between two worldviews in science. The Newtonian approach of physics, which emphasizes the power of reductionism, idealizations, and universal laws that are timeless. And the Darwinian approach, which embraces systems, idiosyncrasy, and evolution, things that are products of time. Neither is better, but both are needed to investigate a world that includes both the timeless and the timeful. I sometimes fascinate about an alternative timeline for the development of the geological and environmental sciences. How different our science and society might be if geologists hadn't been cramped by Lord Kelvin and hadn't been made to feel apologetic about being a time-bound science. Without the heavy doubt about the age of the Earth looming over the field, perhaps geology might have attracted more creative thinkers. Perhaps some of them would have embraced the whole cloth approach to nature practiced by Alexander von Humboldt, an early systems thinker who blithely rejected the reductionism of physics and embraced the natural world in its entirety rather than cutting it into tiny pieces. How wonderful it would have been if Humboldt and Darwin had been more nearly contemporaries. Humboldt was a full generation older than Darwin, and in fact died just months before Origin of Species was first published. Darwin was as much a geologist as a biologist. With his understanding of the power of incremental change over time, and Humboldt's grasp of the geographic diversity of landscapes and ecosystems, there might have emerged a rich form of evolutionary natural science that saw Earth and life as co-evolving systems. The biological and the geological sciences might have blossomed much earlier into mature interdisciplinary fields of inquiry. Of course, there still would have been religious resistance to the implications of Darwin's ideas for human origins. I think the fixation on a certain kind of methodology, specifically one that discounts the importance of time and dismisses evolutionary histories as epiphenomena, was just as limiting for natural scientists. And the implications of this are more than merely academic. Most of the serious environmental problems we face today are the result of the failure in the 19th and 20th centuries to anticipate how new technologies, the internal combustion engine, chemical fertilizers, antibiotics, plastics would interact over time with complex evolving natural systems. And because the public has long been taught to revere certainty, the certainty of physics as the measure of scientific credibility, the inability of geoscientists to speak about things like future climate change in anything but probabilistic terms makes it easy for skeptics to dismiss our work. And perhaps the most unfortunate outcome of geology's late coming of age is that at the time high school curricula were becoming established here in the US and around the world in the 1920s and 30s, geology was not deemed to be an important or relevant area of study for young citizens. As a result, few people, voters, business owners, politicians, journalists, have no clue about how the planet works, in spite of the fact they are constantly, casually making decisions that affect its long-term habitability. But let's get back to our historical narrative. Kelvin's stranglehold on geology finally loosened within a few years of his death in 1907 with the discovery of radioactive decay, which not only provided an explanation for his observation that the Earth was still very hot, but of course also yielded a new approach to determining the age of geological materials, including the Earth itself. Among the pioneers in using natural radioactivity as a geologic clock was Arthur Holmes, one of the most remarkable and I think unfairly unsung geologic thinkers of the early 20th century. Holmes was an 18-year-old physics student at Imperial College in London when he undertook the project of determining the first absolute geologic ages. Starting in 1908, the year after Lord Kelvin died, and just 3 years after Ernest Rutherford had quantified the process of radioactive decay as an exponential phenomenon, Holmes began seeking appropriate rock samples and separating minerals, especially zircon, that were known to contain uranium but no lead at the time of crystallization. He then needed to find the relative concentrations of uranium lead and lead in the mineral, and used Rutherford's radioactive decay law to find how many years had elapsed since the mineral crystallized. At the time he did this, the idea of isotopes had not even been developed yet, and he was measuring element ratios. By 1911, in spite of primitive laboratory facilities and the still rudimentary understanding of the phenomenon of radioactivity, Arthur Holmes had estimated absolute ages of a half dozen igneous rocks whose relative ages on the fossil-based geologic time scale were bracketed by their relationship with sedimentary rocks. 3 samples were from the fossiliferous Paleozoic and 3 from the murky, then undifferentiated Precambrian. Even though some of the lead Holmes measured was not from the decay of the parent uranium, but from another radioactive element thorium, which he didn't know about, his dates are amazingly close to modern values, at least within tens of millions of years. The very first rock he analyzed, a granite from Norway, known to have formed in the Devonian period, based on its cross-cutting relationships with sedimentary strata, yielded an approximate age of 370 million years, which was 18 times longer than Kelvin's estimates of the total age of the Earth. And a Precambrian metamorphic gneiss from Ceylon, now Sri Lanka, was found to be 1.64 billion years old, 2 full orders of magnitude greater. Darwin's intuition was vindicated. Holmes would go on to become one of the preeminent geologists of the 20th century. Kelvin's long-reigning proclamations became irrelevant. Parenthetically, actually, years later, Holmes would challenge another of Kelvin's fundamental assumptions, arguing that the Earth cools mainly by convection in the mantle rather than conduction. Most important, the geologic timescale now could be calibrated. Even the deepest reaches of geologic time could be fathomed. The Precambrian would no longer be an uncharted primordial wilderness. As just a personal aside, I want to mention that I have a strangely close relationship to Arthur Holmes. Holmes's second wife, who's depicted here, Doris Reynolds, who was considerably younger than he was a pioneering female geologist at the University of Edinburgh. She was actually my late husband's PhD advisor, and he was considerably older than I. Although I would love to say that she left an important scientific legacy, she's one of the only women in the long list of men I've mentioned here. The fact is she was one of the last and most ardent supporters of the ill-conceived theory of granitization, the hypothesis that granites are not igneous rocks, but instead formed through fluid alteration of sedimentary rocks. Even Hutton knew better. My husband's PhD on the Donegal granite in Northern Ireland also firmly refuted Professor Reynolds' ideas, and he was her last student. Anyway, after Holmes's pioneering start, instrumentation and methods in geochronology steadily improved over the course of the 20th century, with some interruption during the war years. In 1955, Claire Patterson, another relatively unsung geologic hero from a small town in Iowa, determined the age of the Earth and other objects in the solar system using lead isotope ratios in 2 types of meteorites. This work required an imaginative geochemical vision of the Earth in time, picturing Earth and all the other objects in the solar system as part of one unified co-evolving geochemical reservoir. Patterson spent years trying to get replicable results and finally realized that the problem was ubiquitous lead particles in the ambient environment. En route to finding the age of the Earth, he invented the first positive pressure clean lab and spent the rest of his life campaigning to get lead out of gasoline, paint, and other products. Patterson's determination of 4.56 billion years for the age of the Earth put geology in conflict with the physicists of the day. Again, in 1955, estimates of the Hubble constant, the relationship between the distance to faraway galaxies and the rate at which they are receding from us, suggested that the entire universe was only 1.8 billion years old. That's the age of most of the rocks in my backyard in northern Wisconsin. Fortunately, the discordance didn't last too long this time. Hubble constant estimates steadily improved in the 1960s, and by the 70s, the universe was known to be at least 10 billion years old, and the preferred value is now hovering around 13.8. While Claire Patterson's age determination has stood the test of human time, there is admittedly something dissatisfying about having the age of the Earth come from extraterrestrial objects. For decades, geologists looked unsuccessfully for rocks from the first 500 million years of Earth's existence. And then the discovery in 2001 of detrital zircons in an ancient sandstone in the Jack Hills region of Western Australia became a much heralded moment. So ages as old as 4.4 billion years in some of these detrital grains in the sandstone. And I'll mention again, I have a connection to this milestone in geochronology. One of the co-authors of the paper announcing the age of the oldest Jack Hills zircons was John Valley at the University of Wisconsin, who was on my own PhD committee. And I mention these connections to underscore the human networks in our science, the threads of academic kinship that connect us to other geoscientists in both the present and the past. But now let's step back and ask whether the calibration of the timescale matters really for ordinary Earthlings. The extraordinary antiquity of the Jack Hills zircons and of the Earth itself are profoundly humbling. But I don't think that's really the whole or even the most important message that we should be trying to convey when we talk to students or the public about geologic time. Many people find contemplating geologic time alienating, and it doesn't help that geologic textbooks have for so long flogged people over the head with the 24-hour clock analogy that if the 4.5 billion year history of the Earth were one 24-hour day, we modern humans would appear in just the last fraction of a second before midnight. It's literally true, but I think also fundamentally wrong in its emphasis. It suggests first that we humans materialized out of nowhere, when in fact we have deep evolutionary roots that go back to the wee hours of the geologic morning. Second, it seems to absolve us of our environmental sins. What could we do in that last fraction of a second that would affect the Earth? And finally, it's unintentionally apocalyptic. What happens at the stroke of midnight? Instead, we should emphasize that geology is not so much about time as the power of time to shape, erode, rebuild, innovate, exterminate, transmogrify. And we should start talking more about the geologic future and the idea that we geologists are better equipped than anyone else to lead humankind into that future. I think furthermore, it's useful to adopt the Greek distinction between chronos, which is raw time, billions and billions of years, and kairos, which is time within a narrative. As one starts knowing Earth's history and the vast stretches of geologic time are filled with narratives, protagonists, and plot lines, it's no longer alienating. The characters become familiar, the themes resonant. For me, knowing how to read the narratives embedded within rocks and landscapes enhances rather than diminishes my experience of being an Earthling. Earth has used its time for endless, prodigious creativity, continuously inventing new minerals and rocks, soil, continents, mountain belts, hurricanes, blizzards, tsunamis, microbes, fungi, trilobites, dinosaurs, woolly mammoths, rainforests, coral reefs, humans. Its evolution was never inevitable. Its destiny is not preordained. Indeed, I find the idea of a 7,000 or 8,000-year-old Earth with a short, shallow history positively terrifying, while the enveloping presence of so many ancestors with such a rich anthology of stories to recount is to me deeply comforting. All Earthlings should have some grasp of the intrinsic timescales of geologic processes and our place in the continuum of geologic time. And that's what I mean by timefulness. Everyone should know, for example, that it takes a few tens of millions of years to build a mountain belt and about the same amount of time to tear one down. A few million years for a bipedal ape to evolve the capacity to make stone tools, a few thousand years for an ice age climate to give way to conditions that allowed those clever apes to practice agriculture, and less than a century for them to nudge the planet toward a runaway greenhouse state, empty groundwater aquifers, remove mountaintops, and alter ocean chemistry. In understanding Earth's biography and the wondrous fruits of geologic time, we can perhaps embrace rather than fear the role of time in our own lives. Perception of the true nature of time is the one sense that grows more acute with age. Sight and hearing may fade, but in growing older, one gains respect for the power of incremental change and must come to terms with the fact that there is more than one version of the world. Accepting the reality that we are embedded in time is, in my view, less problematic than the suggestion of some philosophers who assert that time is a human construct, which seems incredibly self-important to me, or some physicists who consider time to be an unexplained problem or some sort of illusion. Both assertions deny the compelling, internally consistent logic of the rock record. And to me, such claims are profoundly dehumanizing since they deny the reality of all our experiences, that time is all too real. For me, understanding our place in geologic time provides a middle way between narcissistic self-absorption and nihilistic despair. It reminds us that we too will eventually be ancestors, so we might as well do our best to be good ones. And that requires making peace with our timeful, temporary nature. I recently heard an interview with the British Pakistani novelist Mohsin Hamid, and at one point he said, "We are all migrants in time." So let us reimagine, re-envision ourselves as the latest in a long line of pilgrims in deep time, en route together toward a common geologic future in the four-dimensional space of timeland. Thank you very much.
Thanks, Marcia. That was fantastic. It was really, really fantastic. We've got some time for questions. You want to?
We have time.
We have time. We have lots of time. Yeah. We typically start with students first, and so we'll take a couple of student questions and then open the floor. And I know Max is looking at the chat, so if there's questions that pop up in the chat, they'll just kind of. And I'll let you. Okay. I'll let you self-direct.
So, if there are students, and if you have questions, I'm happy to.
Maybe an unfair question, so if there's no answer, that's okay. So even now, right, I feel like as we in geology have a better grasp maybe of time, there are still like fundamental divides in geology, right? There are the geophysicists, and then there are the geologists, and then like the biologists who ought to be thinking perhaps about more time than they do but don't. And I'm just wondering, like, I mean, some of the cool science that's happening right now is at the intersection of these fields. Is there like a sort of a, I mean, is time the unifying thing of all of this? Or like, how can we work to bridge that better?
That is a good and profound question. And I think all sciences need to be careful not to splinter into subdisciplines that no longer communicate with each other. It's really the fertile intersections that, because nature doesn't know these disciplinary boundaries that are so important to us. I do think, I mean, almost all geologists, even if you're working in the Anthropocene, time is kind of one of these axes that holds up the world. And I think all of us, you might work across very different time scales, but all of us are trained. This is something that's very distinctive in our training, is we always are thinking about timescales that are longer than the average human. Case in point, I was asked to give a talk a couple years ago, pre-COVID, at the Long Now Foundation. They're the people, Stuart Brand started it. He's sort of the guru of off-the-grid living in the 70s, and now he's this foundation. They're the people who are trying to do the 10,000-year clock. And when I was introduced, the host said that, you know, normally they are the ones who are thinking on the longest time scales, 10,000 years. I was like, 10,000 years. So I think that we're steeped in that, and that's good, and that's a superpower we have, and we should, you know, be proud of that. And I think we should be telling students more about what's hard about geologic thinking. I've thought a lot about this as a teacher. I think the metacognitive habit that geologists do of zooming old sense in and out of timescales is really an amazing thing. We do it so routinely, we don't even think about it. And that's one of the things that makes it hard to become a geologist, and spatial scales as well. Just moving through, like Lyle said, free, like the spirit that animates the universe. I think he captured that idea very nicely. So I think, I don't know, kind of baggy question, answer to your question.
I also forgot to say, because I always do this, I'm sorry, I think this is such a profound and also thoughtful hearing.
Other students?
General questions.
I think Steve had it, he was motioning like,
Yeah,
like
you-
well, it's Peter
Hold it out.
in Dr. Strangelove. Sorry, not, no.
So I want to sort of clarify if I've got a misunderstanding of things, but in Hutton, he sort of was thinking of everything sort of at a constant rate, or did he sort of see things as episodic? And then to go beyond, was Lyle sort of thinking of everything as happening at constant rates? And if so, who would you credit as introducing the concept of changes of rate so that you could have orogeny? In the sense that orogeny sort of implies that there's a change in rate of processes at a certain locality for a certain period of time.
I don't think Hutton ever really talked about rates. He just was so enamored of this idea of busyness. I think of like the children's books, Richard Scarry's Busy Town. It's like everything's doing its thing. The postman is here, but Hutton's view of the earth is like that. Mountains are growing and then they're eroding, and animals are burrowing into the soil. I don't think he was quantitative at all. He loved, it was a philosophical idea, but he also knew how to read rocks. And so I think it's important to kind of acknowledge that he wasn't necessarily a modern scientist, and yet he sniffed something out from the rock record that was real. I think Lyle was more interested in rates, and famously, I think it was in the first edition, I'm not sure, but in one of the editions of Principles, he, for example, charted the migration of Niagara Falls. So he was interested in how quickly the landscape could change. And I don't really know what his view on orogeny, if that was a change of rate or just, sometime this is the time and place we're supposed to have mountains come up. And I don't know.
Well, there's sort of, in the earlier areas of geologic writing, you get the sense that originally the concept of history of the earth and the formation of the earth and the concept of mountain building and everything, they hadn't really separated as separate foci of interest because they didn't have a sense of time, and they had no sense of when mountains were formed relative to when the planet as a whole was formed. So they sort of conflated, and then it gradually separated. But I had the impression, and I probably am wrong, that it kind of took an injection of Cuvier into Lyle to get the modern concept of orogeny, that Lyell's sense of earth processes more uniformitarian, in the sense that uniformitarianism was constant rate, and the catastrophism, of course, was kind of off on a tangent, but it really took the combination of the two. I was just wondering if there's somebody that you credit with really coming up with that.
And I have to admit, I've never made it past maybe 4 chapters in Principles of Geology. It's a heavy lift. The first part is a retrospective on geology up to that point, and then he has this wild analogy with ancient Egypt. What if you imagine that all of the artifacts of ancient Egypt had formed in like 10 years? Then how would you interpret ancient Egypt? Which I think that is trying to capture the public imagination of the day on Egyptology. And yeah, so I'm not really sure. I should know as a structural geologist the history of orogenic hypotheses, but I don't really know. So
I was really struck by your setting up the contrast between the Newtonian science and the Darwinian science.
and again, that's John Hart. There's a nice short paper. It was published in Physics Today some time ago, and I love it. I think it's just right on.
I'll have to check it out. But I was wondering whether the kind of chaos theory and sensitive dependence on initial conditions, revolution in physics, where it sort of becomes like it's not deterministic anymore in the same way that it was for Newton.
That's true.
Whether that kind of
Blasts
Well,
that
I
open. Yeah.
changes how physicists see their science or see the purity of their science.
And I think there is a phrase in physics that's used, path-dependent processes, which is a tiny thing. But I think I would still say those are lesser. It's still like not as precise and pure as the mainstream physics. But quantum mechanics, certainly introduces messy
Weird
things.
stuff.
But it's not necessarily timeful stuff. Electrons don't really have
Well, but I
histories.
guess the chaos theory is
chaos
is
theory,
saying that
right.
It is
Mhm.
it's
Sensitive,
very-
dependent on initial conditions, right.
So it is kind of accidental and it has to go that way.
So I mean, it's not a perfect dichotomy, but I think it helps. It's just useful to have words to explain this. We have a different approach. It's not worse, better. It's just different because these are different entities that we're
Oh, I
studying.
was meaning like, does physics have to confront the
Oh,
reality?
I
that
see,
That's not
yeah.
how the world really
Right,
is.
right.
I
Yeah.
guess. Thank you.
I have one from the chat,
Okay.
from Paul Dingsberg. Really interesting talk. Did paleontology more or less grow up alongside geology with similar styles of thinking, e.g. needing lots of time to explain observations?
Yeah, well, it depends on when we're talking. So geology really did start as stratigraphy, I would say, of looking at strata. And William Smith's famous ability to correlate strata was about paleontology. And so when people were looking at rock units and then could gradually correlate them over wider areas using fossils, then paleontology became the heart of geology. But as I said before, even Smith, I don't think, was interested in evolution. He wasn't thinking that his ammonite fossils and the units that he used to map England were a record of evolution. He just recognized there were distinct shells. So I don't think initially paleontologists universally accepted the idea that there had to be lots and lots of evolutionary time. So I'm not sure if that answers the question. It was only really when Darwin, I mean, people were thinking about evolution before Darwin. Even Darwin's grandfather, Erasmus Darwin, was thinking about evolution, but the mechanism of evolution by natural selection is what Darwin had. And then it became clear, if he's right, we need a lot of time if everything has evolved from one common ancestor. So I think there probably were different worldviews, even as people were beginning to do geologic mapping and stratigraphy. Initially, maybe it could have been all fit within the biblical framework. Bruce.
Excellent talk, thank you. So I guess one thing I wanted to ask you is, when I see that, and think about Hutton Lyle and the manifestation through time of science, I always think how also constrained it is by technology availability and funding. Because you look at something like Tycho Brahe, right, he got 25% of Danish GDP, so he could build that observatory on the Isle of Ben, between Sweden and Denmark, and then Kepler was one of his students. And then they got into a race with each other, and then actually Tycho Brahe got the right structured universe. At the last moment, the king of Denmark said, "You've got to put the Earth in the middle because I've just given you 25% of the time to do this." Right? So and that's why Kepler was able to go. Otherwise, the word Tycho Brahe would have been on our lips instead of Kepler, right? So that's kind of one thing. And then the other thing is, I think about von Leeuwenhoek and taking your glass bead on a brass plate, that kind of thing. But I'm just thinking, like Hutton, if you would have had a good compound microscope, you would have not been constrained. I mean, you're saying a lot of constraint on things that kind of with this mix of the spirituality or social religion things. And you're exactly right; they're all mixed. But at what level could it just simply be they didn't have the right tools?
Well, absolutely
right?
true. That's true too. But you can't even imagine the tools you need if you can't imagine the questions.
Well, see, my
So-
son wasn't short on questions.
Yeah.
So, I would argue that if you were to throw, say, a 1896 compound microscope into the hands of Hutton, he would have done much bigger things. It just seems like, right? So it's just interesting to think about this beautiful progression you laid out, and if you start bringing in the constraints of funding and technology, and what that combination. I don't know, was Hutton self-funded or did he? Get
Well,
money?
he was of the aristocracy. And he was on the kind of margins of the Edinburgh Enlightenment. He knew James Watt, and I think the philosopher, is it David Hume?
Yeah.
And Ben Franklin apparently even dined with him once. So he was wealthy. He was, just musing about things, walking about the landscape. So he didn't need a lot of funding. He needed companions who would carry his stuff with him, probably. But I mean, Holmes is a good illustration of what you're saying. The minute radioactivity was discovered, this 18-year-old kid was saying, we can use this to date rocks. So you're right, they go hand in hand.
Maybe time for one more question, or two more if they're burning.
Yeah.
Well, a couple, it just popped in my mind as you were saying that. I mean, Rutherford also recognized that you could use it to date the Earth. I believe he also tried.
Did he try to date rocks, actually?
I'm not sure of that.
Maybe he was doing helium dating, actually, which now we've come back to.
Yeah.
Right, I think he did, yeah.
But, he did try to do it, and he actually gave a paper. I thought he gave a paper with Kelvin in the room. I'm not certain of that.
I've heard that, and I've
And
had,
that might be full but
and that Kelvin was snoozing in the back.
yeah, I've heard that.
Yeah, he presented a paper in 1905. It was a uranium helium date, and it was the first radiometric date. And it was a sample of Fergusonite from Connecticut, which was really high uranium bearing mineral. And he came up with an age of 400 something million years. But even at that time, it was recognized by him, his collaborator Sadi, that helium was not a great daughter product because it was easily lost from the crystal. So even back then, they kind of recognized that in principle, he showed in principle that you could do it. But it was certainly the uranium lead dates that were more reliable because you didn't have to confront the problem of helium mistakes.
Which now, we exploit Willie's own research.
So my other question is actually going back to Hutton, and hopefully you can give them a little latitude there. I'm looking for you to do this. When I always read that quote of no best at the beginning of prospect of an end, I always interpreted that from the perspective of someone who had no concept of how long Earth actually was, and it still holds true today.
That's
in a sense, we have no evidence of the beginning of Earth, nor do we have any idea when it's actually going to end. We have ideas, right? So that still holds true. And I would just wonder, being of the landed gentry, a member of the Scottish Society, the honorsness of the Scottish Church at the time, perhaps he felt constrained to, in the same way that others who preceded him were constrained. And so my question then is, are the contemporaries of this that would have said, couch their scientific finding without having divine guiding him?
That he was just a man of his time. And
Yes.
I don't know. When I read Hutton, I see just this kind of ebullience to his writing. He was just excited to have recognized something.
He was
I
supposed
don't
to be
see
a
him
really
as someone
great
who's
guy to be with.
Yeah.
He's like the guy at the bar who buys everybody drinks and
Exactly. I
everyone
can just
wants to talk to
imagine
him.
him. You
He
just
can
wouldn't
talk about
stop talking.
anything.
Yeah. So
Like Steve Marcia.
so I don't know. Who knows?
I'm fearful, I'm fearful because I think he was such a, as you pointed out, such a great pioneer, such a great thinker, such a contributor to the modern progression of our science. All that he did today, or his version of something that may not really.
Yeah, and I don't see it as a besmirchment. I just think we need to be honest with ourselves about where people were coming from in their historical moments.
But it's certainly on a human time scale, Earth is rather infant. If they can put a limit to that concept, it is, right? From our way of thinking, we can't even truly conceive of 4.5 billion years. Right? This is the reason for all these diagrams. And that was my third question. Have you got a good way of trying to help students conceive of the depth of time?
Well, not the 24-hour
That's
clock.
not a good one, no. I've asked them to try and asked them to calculate how long it would take to count that time. You get about 177 years if you can count one number every second, which is not possible.
And we have things like measuring things out in the hallways and
Yeah.
getting that sort of thing. But I think it's more really going into the field and in Wisconsin, we have all sorts of lovely things like eskers and lying on top of Silurian coral reefs and getting them to start understanding, well, this thing formed a while ago, this thing formed quite a while ago, and then we got these igneous rocks that formed really quite a long time ago,
Yeah.
and just getting that sort of what I call temporal proportion.
Mm.
But it takes time.
Scale
It's a skill that has to be.
Scale and the proportion is the hard thing.
It is. And actually, your questions made me think of a better answer to one of Steve's questions, which was that there was one case that I know of that Hutton tried to do a quasi-quantitative calculation, and that was he knew of Hadrian's Wall. That's the border between Scotland and England, and he knew that it was about at that point 1700 years old or so, and that it was hardly changed since Roman times. People had pilfered blocks out of the wall, but the rocks themselves were hardly eroded. So then he said, if you're going to erode a mountain belt down, it would take so much longer. And here's this almost 2,000-year-old thing that's hardly changed. So that was one quasi-quantitative thing that he did. But I still don't know about the orogeny question. Okay, thank you so much.
Yeah. If you would like to stick around, there's items available in the reading room to look at, and then there's also the exhibits, which we can all take a look at as well. Thanks, everyone.
I am the only person in this room who has read Doris Reynolds' paper.